Hello everyone, today we are going to do with electromagnetic waves. So let's begin with the chapter. It's a chapter of physics in class 12 NCERT part 2. For electromagnetic waves today, let me first link the chapter to the history of electromagnetic wave. We will go with the year, we will go back to the year 1831 when Faraday stated that change in magnetic flux linked to a coil induced an EMF in the circuit linked to it. Change in magnetic flux linked to a coil induced an EMF, which is electromotive force, in the circuit linked to it. This is just the principle of working of AC generator, where there is a change in the magnetic flux linked to the coil and EMF is generated and the power is, or electric current is flown through the circuit, which is the load. So Faraday stated in 1831 that change in magnetic field linked to a coil can induce an EMF in the circuit, and according to Faraday, he gave this EMF is equal to E equal to minus d phi by dt. Right? From the chapter of AC currents, we are familiar with this formula. E is the EMF induced in the coil is equal to minus d phi by dt. What is d phi? D phi is the rate of change of flux. Okay, and T is the time. So, what did I say? We went back to the year 1831 when Faraday stated that change in magnetic flux linked to a coil can induce an EMF in the circuit. Okay, linked with the coil. Okay. Now, the question arises, can change in electric field, E vector means electric field, generate magnetic field? This is my question. Since change in magnetic field can generate an electric field in the coil, now if we reverse the question, can change in electric field generate magnetic field? Yes, the answer is yes. Okay. Okay. Now who said this? Change in electric field can generate a magnetic field was said by James Clerk Maxwell, who is the main subject or the main man behind this chapter of electromagnetic waves. James Clerk Maxwell said and proposed that change in electric field can generate a magnetic field. Okay. So what did I say up to now? We went back to the year 1831 when Faraday stated that change in magnetic flux linked to a coil can generate an EMF in the circuit linked with the coil. Then question came, can change in electric field generate or induce any magnetic field in the coil? The answer is yes. Who said this? This answer was said by James Clerk Maxwell, who became the main subject of this chapter of electromagnetic waves. Okay. Now, the people or the scientists of the stone time asked James Clerk Maxwell, how is this possible? How can change in electric field generate a magnetic field? So, now we will come to the next part, or the experiment performed by Maxwell to prove his point that change in electric field can generate a magnetic field. Okay, so let's do it. I have to clear out the board. Okay, give the heading Maxwell experiment. What did James Clerk Maxwell do to prove his point? What was his point? His point was to prove that change in magnetic electric field also produced a magnetic field. Okay. James Clerk Maxwell, I give the heading Maxwell's experiment. Okay. Maxwell's experiment to prove his point. What did Maxwell do? Maxwell took a circuit like this. Okay, this is a cell, this is a switch or key, this is a parallel plate capacitor. Okay, now let me do a thing. Make it positive terminal and make it negative terminal. Okay, now the switch is open, no current or any charge flow occurs in the circuit. Now when the key is closed, okay, the current will start flowing in the circuit, right? Current will flow in this direction, I, and here also I. Okay, as a result, negative charge will come, means current is flowing this direction, so negative charge will flow in this direction, right? Okay, so negative charge will flow in the opposite direction of the flow of current, right? I was sorry. Current is flowing in the direction, so negative charge will flow from this side to this side, okay? So this side of the capacitor will get a positive charge, right? And negative charge is going from this side of the capacitor to this side, so the capacitor of that side, the plate of the capacitor on the other side will get negative charge, right? So Maxwell considered a charging parallel plate capacitor. Okay, now he considered two regions. Suppose this region is X, I circle this, and this region inside the parallel plate capacitor is Y. Okay, now Maxwell said that at X means at this point, by Ampere circuital law, right? We are familiar with Ampere circuital law. By Ampere circuital law, we can say that surface integral of B vector dot ds vector equal to mu 0 into I, correct? This is the Ampere circuital law which we get from the magnetic induction, right? And at Y, I do it here. At Y, by Ampere circuital law, I am giving by ACL. Okay, surface integral of B vector dot ds vector equal to mu 0 into I. But see, here is no medium to conduct the current, right? Between two parallel plate capacitors, there is just empty space, nothing to conduct, means no material to conduct the current, right? No continuity between the two plates of the capacitor, so there is no current naturally, so this I becomes 0, so B naturally becomes 0 inside the capacitor, since I equal to 0 between the plate of the capacitor, there is no continuity, so I equal to 0 according to Maxwell by Ampere circuital law. Okay, but this is actually not happening because the circuit is complete and the current is gradually flowing and charging the capacitor. As a result, the current is flowing in this direction, so a negative charge is being beared on that plate and a positive charge is being produced in this plate. Okay, but so that means that Ampere circuital law is insufficient to explain the continuity between the two plates of a capacitor, right? So Maxwell said that this thing is not correct, means this thing is insufficient to explain the continuity of the current between the two parallel plates of the capacitor. Okay, now what did Maxwell do? Maxwell brought the idea of displacement current. Okay, I am doing it again. I will draw the circuit. I explained you why Ampere circuital law was insufficient in explaining the continuity between the plates of a capacitor. Continuity of current between the plates of a capacitor. Now, Maxwell brought the idea of displacement current. Okay. So we draw a circuit again here. Circuit was going like this, no need to draw the entire circuit. So this was the parallel plate of the capacitor. This side was getting a negative charge and this side was getting a positive charge. So current was flowing this direction and the key was closed, right? Okay. Maxwell brought the idea of displacement current. Maxwell said that not only current carrying conductor produced magnetic field, but now wait, we can see that this when this key is closed, okay, and here was my cell and here was my cell, plus charge and negative charge, okay, current is flowing. Now current can only flow through a circuit when the circuit is complete, right? But we cannot find any medium of continuity between these 2 points of a circuit, between this point and between this plate of the capacitor and this plate, okay? That means something must be here. Something must be here for which the circuit is complete. Otherwise the current should not flow, right? So the only thing which is changing gradually between these 2 plates of the capacitor is the charge. Means this plus charge is gradually increasing and this minus charge is gradually increasing. So what happens? There is a net change of electric field between these 2 points, right? For which a current is flowing, right? So Maxwell said that not only current carrying conductor produced magnetic field, but also a changing electric field in vacuum or free space also produced magnetic field. Okay. Now, is this magnetic field produced? What is the proof for that? The proof for that is Maxwell took a magnetic needle and brought between these 2 plates of a capacitor. He found that magnetic field got deflected. That means there is a change in magnetic field gradually, right? So Maxwell said not only current carrying conductor produced a magnetic field, but also a changing electric field in vacuum or free space because between these 2 plates of a capacitor there is a free space or a vacuum, means nothing is there, right? So a change in electric field in vacuum or free space also produced a magnetic field, right? Maxwell called this current, and this magnetic field was the source of the conduction of current. Means this magnetic field was produced gradually, and for this magnetic field a current was being produced between these 2 plates, which is called displacement current. And this magnetic field produced a current called displacement current, which is denoted by ID, produced ID, which is my displacement current, right? Now, what is the expression of the displacement current? So, expression means how to mathematically find out the relation or the mathematical expression of this displacement current. So Maxwell, by plotting equation and finding and doing a lot of research work, Maxwell came to the conclusion that this ID is the displacement current. This ID is equal to epsilon naught into d phi e by dt. This came from experiments. Okay. So from experiments, Maxwell find out that ID equal to epsilon naught into d phi e by dt. Okay. So this was about the idea of displacement current, which is produced between two parallel plates of a capacitor, right? So let's come to the definition of displacement current. Okay, I write this notation here. ID equal to epsilon naught into d phi e by dt. I keep it here. Okay, I have to erase this part. So according to Maxwell, a change in electric field is produced here, for which a magnetic field was being generated, and for this magnetic field, ID or displacement current was being generated here between these two plates of a capacitor, for which the circuit was complete. Now this ID, he said, is different from this IC. Let me assume that this is IC, means the current through the conducting wire. Now this ID is different from this IC. We will now come to the definition of displacement current. Okay, definition. What is displacement current after all? Means the definition of displacement current. The current due to change in electric field between two plates of a capacitor. Right? As I have said, between this current due to the change in electric field is continuously being changed between two plates of a capacitor is called the displacement current. Okay. Now this thing also solved the continuity of the current between these two plates of a capacitor, because at that time, means 1831, I am repeating again. So by 1830s, you can see there was a big question about how is this, means what is the continuity of current between these two plates of a capacitor. So there was a scientist called Maxwell who said that ID, or the displacement current, which is different from the conductor current, is flowing between these two plates of a capacitor, for which there is continuity between the plates of a capacitor in a circuit. Right? So the idea of displacement current was able to solve the continuity of current or the circuit between the two parallel plates of a capacitor. Okay. Now Maxwell did something. Maxwell's main aim was now to find out. Maxwell's main aim was to find out whether the magnetic field produced by this displacement current and this conductor current in the conductor is similar or not. So for that he took a magnetic needle again. Okay, he placed a magnetic needle here. He find out the deflection caused due to the magnetic field which was being generated. See, like this, we know right hand thumb rule. This is the direction, means current is flowing in this direction inside the circuit. If the current is flowing in this direction. So if we hold it like this, so this direction means anti-clockwise direction here, right? And same thing he did over here. He placed the magnetic field. He saw that the magnetic field due to displacement current and the magnetic field due to the conductor current is similar. So from this we come to the conclusion that this was my B X location, right? And this was my Y location. So Bx equal to By. So similarly IC equal to ID, because it has to be equal, because actually the current is producing the magnetic field, no? So for continuity, if the magnetic fields of a two places are equal, so the current will also be equal, because the current which are producing it should be equal for continuity, right? This means that the magnetic field produced due to the conductor current and magnetic field produced by the displacement current is equal, right? So this was performed by Maxwell. So this was from the experiments he found out this. Now we will prove by mathematically how this IC is equal to ID. Okay, let's now find out how this IC is equal to ID. Okay, for that I have to clear out the board. Our now objective is to find out how that IC is equal to ID. Proof. IC equal to ID. Okay. From current electricity we know that IC equal to dq by dt, right? Rate of flow of charge to the cross section of the conductor, right? I keep this aside for the time being. IC equal to dq by dt. From current electricity we know this. Okay. Now this ID, I take this ID. ID equal to epsilon naught into d phi e by dt. I draw two plates of capacitor. Okay. This is my IC, this is ID. Okay. Negative, 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 positive, positive, positive. Okay. This capacitor plates of a capacitor are charging gradually. Okay. Now this phi E. Now this phi E we know. Phi E equal to EA cos theta. In this case the cos theta is 0 degree, right? So I take cos 0 degree equal to EA. Phi E equal to EA, and the electric flux, electric field through the entire area, right? So I put this value here. Epsilon naught into d phi E. So d EA by dt. Okay. Now from electrostatics we know that this E, or the value of E, this is a conducting line, right? From electrostatics we know that from electrostatics we know this E equal to sigma by epsilon 0. Now what is this sigma? Sigma is a charge plus charge per unit area equal to Q by A into epsilon 0, right? This epsilon 0 just got multiplied with the area. Sigma equal to epsilon 0, right? So I do nothing, I just put the values over here. So epsilon 0 into D. E is Q A epsilon 0, Q by A into epsilon 0. Right. Let's do it a little bigger. E0 equal to D into Q by A into epsilon 0 into A by dt. Now see, this A and A is cancelling out, right? Let us cancel this A. Okay. Now this is epsilon naught is constant, so it will come out, right? So epsilon naught into dq by and this epsilon naught also comes out because it's constant into dt. So epsilon and epsilon cuts out, and what do we get? id equal to dq by dt. Yes. And what is my dq by dt? My dq by dt is IC, which is the conductor current. So I am doing it here because of lack of space. Let's give an arrow here. id equal to IC. Hence proved. Okay. Now summarizing the entire thing. Maxwell said that id equal to d phi e by dt. Okay. D phi is the change of electric flux per unit area. Okay. Electric flux and electric field is same. So it is EA cos 0 degree. Why 0 degree? Because the plates are parallel to each other like this. Okay. So it becomes EA because cos 0 degree is 1. Now from electrostatics we know that this EA equal to sigma by epsilon 0. Sigma is a charge per unit area, right? So I did nothing, I just read Q by A into epsilon 0. Okay. Now I did nothing, I just put up this value and substituted it here. Okay, first I wrote d phi A, I wrote dEA by dt, and then I put that value over here. So I can find out that this A and A got cancelled out gradually, and this epsilon naught, since it is constant, so it comes out of the differentiation, so and gets cut and gets nullified, or means cancelled out because of this epsilon 0, right? And what is the remnant part is a dq by dt. I wrote it there. Now this dq by dt, from current electricity we know that it is the current in the conductor, so we get id equal to IC. So this was the proof of conduction current equal to my current due to the displacement current. Okay. Now Maxwell's already said that there was something wrong in the Ampere's circuitous law, right? And so he said that Ampere's circuitous law was insufficient in explaining the continuity of current inside the parallel plates of a capacitor. So he made some modifications in the Ampere's circuitous law. Okay. For that I give the heading. For that I give the heading modification with modification of ACL. ACL means Ampere's circuitous law. Okay. Modification of Ampere's circuitous law. I again draw this parallel plate of capacitor. I consider this region to be my X and this region to be my Y. Both the cases in here current IC is flowing and this one is ID. Right. So by ACL at X he said that he said that Ampere was correct at X B surface integral of B vector dot ds vector equal to mu 0 into IC is the current to the conductor, but he modified the relation at Y. He said surface integral of B dot ds vector B vector dot ds vector equal to mu 0 into id. This is what we found because id is the current flowing here, so mu 0 into id. So modification, I'm writing it here. Okay, now I will do the net modification which was performed by Maxwell. Maxwell did nothing, Maxwell just added up the two equations. Here was my 1, this was my 2. Okay, so B vector dot ds vector equal to mu 0 IC plus mu 0 ID. This is what we found here, right? Now we can take mu 0 common, and we always know that ID equal to sigma, that ID equal to my epsilon naught by d phi by dt, right? Yeah, I erased it by mistake. ID equal to epsilon naught d phi e by dt. Okay. Now let's make some changes to this. I make common of the mu 0 and write it IC plus epsilon naught d phi e by dt. This is very important. This is called modified ACL or modified Happier circular law according to James Clerk Maxwell. James Clerk Maxwell was an excellent physicist. Because of this discovery and many other discoveries that were there. Okay. Now, James Clerk Maxwell also said that the electric field which was generated was always magnetic field was perpendicular to the magnetic field, and the magnetic field which was also generated because of the electric field was perpendicular to it. Okay. Okay. So Maxwell said proposals, no, it was not a proposal, it was stated, means inference. Okay. Maxwell said that the electric field produced was perpendicular to the magnetic field and vice versa. Vice versa means just the opposite. Okay. So this was about the idea of displacement current and the electric field was produced, and okay. Next we come to Maxwell's equation. Maxwell said that all the basic principles of electromagnetism can be explained by the 4 fundamental equations, okay, called the Maxwell equation. Okay, wait, let me write it here. Maxwell's equation. Maxwell's equation. Okay. Maxwell stated that all concepts or all principles of electromagnetism, electromagnetic waves, or electromagnetism in this case. Now we have not introduced any wave like that now. Okay. All principles of EM or electromagnetism can be explained PLAINED explained by 4 equations called Maxwell's equation. Now you have to keep in mind that the upcoming 4 equations, okay, yes, I will write 4 equations just now. These equations were not discovered by Maxwell. These were discovered by some other scientists, famous scientists rather. Maxwell just said that he did not discover any of the 4 equations, but all the basic principles of electromagnetism can be explained by these four fundamental equation which defines the entire electromagnetism. Okay, the first equation which comes is the Gauss law of electrostatics. Okay. Now what does Gauss law say? The surface integral of the entire total charge in a closed surface is 1 by epsilon times of the total charge enclosed. Okay. So according to Gauss law, we can say that phi E into Q by epsilon 0. Right? So we can say that surface integral of E vector dot dA vector dA, surface integral of A vector dot dA vector equal to Q by epsilon 0. Gauss law of electrostatics. Okay. The second one which comes is, I am writing this for the time being, Gauss law of magnetism. Gauss law of magnetism. What does Gauss law of magnetism says? The internal magnetic flux inside a closed surface is 0. Okay. Now the next thing which comes is Faraday's law of electromagnetism, which is the basic, the main, from where the concept came. Faraday's law of EM. EM means electromagnetism. Okay. And lastly is modified with Ampere's orbital law. Modified is the one which was later modified by Maxwell, means the ID one. Okay, mu 0 into ID, modified ACL. Maxwell stated that all these 4 equations, okay, all these 4 fundamental equations rather, explain the entire principles, fundamental equation. Okay. Fundamental equations for electromagnetism. Maxwell said that this all 4 equation was sufficient for explaining the electromagnetism. Okay. So keeping today's lecture up to this much, next day will come about conduction current. Till then wait for it. Have a nice day. Thank you.